everyone and welcome back to Study Room. In the previous lecture, I taught you the various laws of exponents and we even learned its application using various numerical problems. In today's lecture, I'll be teaching you how to use exponents to express small quantities in standard form. So let's get started. The very first thing that I'll be teaching you is interconversions between standard and normal form. So exponents can be used in this method. But let us first realize, why do we need to convert normal forms to standard forms? This is the first thing that we need to know, that why do we need to do this? So let us observe the following fact. The first fact given is that the distance from the earth to the sun is 1496,000,000 meters. The speed of the light is 300,000,000 meter per second. The thickness of the book is 20 millimeter. The average diameter of a red blood cell is 0.000007 millimeter. So, did you observe something? I observed. It is facing a lot of inconvenience when we are trying to read out either very small quantities or very large quantities in normal form. It's consuming a lot of time, as well as it's a bit inconvenient. So this is the need of exponents. We need exponent to express these very large numbers or very small numbers in standard form. So now let's learn how to use exponent to represent these large or small numbers in standard form. Now let's talk about the first case. That is, if we have a very large number, how to represent it in a standard form. So in this case, what we do is we take the decimal place towards the left. And in doing so, the number of places we'll be taking to the left will represent the exponent. That means, let me explain this with an example. Over here we have this quantity. So the decimal place is over here actually. The decimal is over here. So what happens is that we have to take this decimal place over here. So we are shifting the decimal place towards the left hand side and we are shifting 11 places towards the left hand side. So this can be represented in the standard form as 1.5 multiplied with 10 to the power of 11. So we can say that when we are representing larger numbers, then this exponent will be positive. And we have to shift the decimal towards the left hand side, and the number of places we will be shifting the decimal will become the exponent of 10. Now let us take the second case. That is, when we have to use exponents in order to represent very smaller quantities or numbers in standard form. So in that case, what happens? We have to shift the decimal place towards the right hand side. Now in doing so, the number of places we will be shifting towards the right hand side will become the power of 10, will become the power of the exponent. But here there's a change. The power will take a negative sign. Let me explain this with the help of an example. For example, if we have this number 0.000007. Now in total we have 1, 2, 3, 4, 5 zeros. Now what we'll do is we have to express this in standard form. We will shift this decimal place towards the right hand side. So we have to shift it 1, 2, 3, 4, 5, 6 places towards the right. So this will be expressed in standard form as 7 multiplied by 10 to the power of minus 6. This minus sign will be taken because we are expressing smaller number. So in expressing smaller number, the decimal shifts towards the right hand side and the exponent takes a negative sign. It will always take a negative sign. And another important thing is that the number of places this decimal will be shifted will become the power. That is, we have shifted 6 places towards the right. So the power of 10 will be 6 and it will be taking a negative sign. Now that I have taught you the basic rules, let us try expressing the given numbers in standard form. So the very first number we have over here is this. Now observe this number. This is a very small number. So in case of small number, we have to shift the decimal place towards the right hand side. And in case of small numbers, when we are shifting the decimal place towards the right hand side, what we had to do? The exponents will always take a negative sign. So remember this and try finding it out. So the standard form of this will be, we have to shift this decimal place towards right. Now let us check how many places we are shifting. We are shifting it 1, 2, 3, 4, 5, 6, 7. So basically we'll give the decimal over here. So we are shifting 7 places. So the answer will be 5.64 into 10 to the power of minus 7. This will take a negative sign because the decimal is shifting towards the right hand side and the point will be over here. So the standard form is 5.64 multiplied by 10 to the power minus 7. Now this is a similar case where we have a very small number and we have to shift the decimal place towards the right hand side. So we have 1, 2, 3, 4, 5, 6. We are shifting 6 places. So the answer will be 2.1 multiplied by 10 to the power of minus 6. Now observe this number. This is a large number. When we have to express large number in decimal in standard form, then the decimal point is over here. It's basically over here at the end of the number. And we have to shift this decimal point towards the left hand side. Now let us calculate the number of places we are shifting. So 1, 2, 3, 4, 5, 6, 7. We are shifting 7 places. So the answer will be 2.16 multiplied by 10 to the power of 7. The power will take a positive sign, not a negative one this time. Now, this is again a similar case where we have to shift the decimal place towards the left hand side. So, the number of places we have to shift is 1, 2, 3, 4, 5, 6, 7. 7 places. So, the answer will be 1.524 multiplied with 10 to the power of 7. Now, we have to represent all the facts that I read out to you in standard form. So try recalling the first fact that I told. That was the distance between the earth and the sun. It was somewhat 1496000. Like in total we had 1, 2, 3, 4, 5, 6, 7, 8 zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8 zeros. That was the distance between the sun and the earth, and it was given in meters. Now we have to represent this in standard form. In order to do so, we have to shift the decimal place towards the left hand side. So number of places that will be shifting is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the exponent will take 11. So it will be 1.496 multiplied with 10 to the power of 11. The second fact that I told you was the speed of the light, and it was 3 and then 1, 2, 3, 4, 5, 6, total 8 zeros were there. So 1, 2, 3, 4, 5, 6, 7, 8 zeros. And this was meter per second. This was the speed of the light. Now in order to represent it again in the standard form, we have to shift the decimal place towards the right hand side. And the number of places we'll be shifting is 1, 2, 3, 4, 5, 6, 7, 8. 8 places. So this can be written as 3 multiplied by 10 to the power of 8 meter per second. The next thing that was given to us was 20 millimeter. Now this 20 millimeter can be expressed in standard forms in two ways. First is, we can shift this decimal point just a single place and write it as 2 multiplied by 10 to the power of 1 millimeters. Or the second thing we can do is, we can even express it in the form of 0.2 multiplied by 10 to the power of 2. Because we are shifting the decimal place towards the left hand side. So the power will be 2 and we are shifting it 2 places. From here we are shifting it 2 places. So it will take power 2. Now the fourth fact that was given to us was 0.000007. This was the quantity that was mentioned in the fact and it was given in millimeter. We have to convert it in the standard form. So what we'll do in this case? In this case, we have to shift the decimal place towards the right hand side, not left hand side this time. So when we have to shift the decimal place towards the right hand side, we have to take the exponent negative. So first it will be 10 multiplied by, calculate the number of places we are shifting, 1, 2, 3, 4, 5, 6. So it will be 10 multiplied by 7 multiplied with 10 to the power of minus 6, because we are shifting the decimal place towards the right hand side. So it's 7 multiplied by 10 to the power minus 6 millimeters. Now I'll be teaching you comparing very large or very small quantities using exponents. When we have two quantities that are very small and we have to compare them, what we do is, we at first calculate the standard form of those quantities and then divide them. Let me explain you with the help of an example. So we have the diameter of the sun given as 1.4 multiplied with 10 to the power 9 meters and the diameter of the earth as 1.2756 into 10 to the power 7 meters. So these are very large quantities. So exponents are used in case of very large or very small quantities. So how can we compare these two quantities? So what we'll do is we will first convert it in standard form and divide. So basically the sun's diameter is 1.4 multiplied with 10 to the power of 9. And let us divide this with the diameter of the earth, that is 1.2756 multiplied with 10 to the power of 7. Now let us leave this as it is, 1.4 into 10 to the power 9. Now concentrate on the diameter of the earth that has been given to us, that is 1.2756 into 10 to the power 7. Let us try shifting this decimal place 2 places towards the left hand side. So what we are doing is we are shifting this decimal place 2 places towards the left hand side. So this quantity will become 0.012756 multiplied with. Now I told you whenever we are shifting the decimal place towards the left hand side, then with this exponent will be taking a positive sign, and the power of this exponent will take up the number of places that we are shifting. So the number of places we are shifting is 2. So this 10 will take up value 2, and we already had 10 to the power of 7. So this will be multiplied with 10 to the power of 7. Now this numerator can be written as, I am writing it over here. So this numerator can be written as 1.4 multiplied with 10 to the power of 9, and it is divided by 0.012756 multiplied with. Now observe over here, 10 square and 10 to the power of 7. Bases are same, powers will be added. That means 7 to the power of 2 plus 7, 10 to the power of 2 plus 7, that is 10 to the power of 9. So we get 10 to the power of 9 over here. Now this 10 to the power 9 of the denominator gets cancelled out with the 10 to the power of 9 of the numerator. This is the reason why I converted this in the standard form. Like it was already in the standard form, but what I did was I took the decimal place 2 places towards the left hand side in order to increase the value so that it gets cancelled up completely. So now we are left with 1.4 divided by 0.012756, which is approximately equal to, like when we'll calculate it, divide these two quantities, this will be approximately equal to 110. So from here we can conclude that the diameter of the sun is nearly equal to 110 times the diameter of the earth. So this is the way to compare these two large quantities. Now let us try doing another example of the same sign. So let us compare the size of a red blood cell to that of a plant cell. In the previous question, we compared the diameters of the sun and the earth. In this question, we will be comparing the size of the red blood cell and the plant cell. So what we have to do? We have to convert the sizes in standard form and then divide them. Now, the size of the red blood cell is given as 0.000007. So in standard form, this quantity can be written as 7 multiplied by 10 to the power of minus 6 meters. Why? Because I am shifting this decimal place towards the right hand side, and the number of places I am shifting is 6. So the decimal will be 10 to the power of minus 6, negative sign, because I am shifting it towards the right hand side. Now we have the size of the plant cell as 0.00001275. Now we'll be converting them into standard form. So by converting it in standard form, we get 1.275 multiplied with 10 to the power of minus 5 meters. Now in order to compare them, we have to divide both the quantities. That is the size of the red blood cells divided by the size of the plant cell. So we get 7 multiplied with 10 to the power of minus 6 divided by 1.275. This is 1.275 multiplied with 10 to the power of minus 5. Now we will be using the property of exponent over here. The bases are same and they are divided. So the powers will be subtracted. Other things remains the same, that is 7 divided by 1.275 remains the same. Only this part, that is 10 to the power of minus 6 divided by 10 to the power minus 5, we can write this part as 10 to the power of minus 6 minus of minus 5, which gives us plus 5, because we are subtracting the powers. So here we will be getting 7 divided by 1.275 multiplied with 10 to the power of minus 1, because minus 6 plus 5 gives minus 1. which is equal to 0.7, because 7 multiplied by 10 to the power minus 1 is 0.7 divided by 1.275. Now when we divide these two quantities, that is 0.7 and by 1.275, this is approximately equal to 0.5, which is also written as half. So from here we can see that the size of the red blood cell is half the size of the plant cell. So this is the conclusion, and in this way we measure very large quantities or very smaller quantities. Now let us try doing another example. The mass of the earth is given as 5.97 multiplied with 10 to the power 24 kgs, and the mass of the moon is given as 7.35 multiplied with 10 to the power of 22 kg. Now we have to calculate the total mass. So the very important concept when we have to add the exponent is that we have to make these exponents same. That means if we have 10 to the power 24 over here, this quantity also needs to be made 10 to the power 24, because it will provide us convenience in calculating and adding up both the quantities. So when we have to add the numbers in standard form, we convert the numbers into the same exponent. So this is a very important thing that we need to keep in mind. So let us convert this 7.35 into 10 to the power 22 as this form, like in this form, that is 10 to the power of 24. So this can be written as 0.0735 multiplied with 10 to the power of 24. What I did is, I took this decimal and shifted it 2 places towards the left. When we shift this decimal 2 places towards the left, this quantity becomes 0.0735, and I'm shifting it 2 places towards the left. So I'll have a 10 to the power of 2. When this 10 to the power 2 gets multiplied with 10 to the power of 22, both of them gets added up. So we have 10 to the power 22 plus 2, that is 10 to the power 24. This is the simple conversion of this quantity into a standard form of this type, where this exponent part will be same as the exponent part of the mass of the earth. Now let's add them up. So we have to add 5.97 multiplied with 10 to the power of 24 with 0.0735 multiplied with 10 to the power 24. Now the convenience that we'll have is we can take this 10 to the power 24 common from both the terms. So we'll take 10 to the power 24 outside, and this is the common from both the terms, and we are left behind with 5.97 plus 0.0735. Now this is a simple decimal addition. So we have 10 to the power of 24 multiplied with, adding these two quantities up, we get 6.0435. So our final answer will be 6.0435 multiplied with 10 to the power of 24. So we can say that this is the sum of the mass of the earth and the moon. Now let us try doing an interesting problem. During solar eclipse, the moon comes in between the sun and the earth. So let's say this is the moon, it comes in between the sun and the earth. Now, the distance between the sun and the earth has been given to us, that the distance between the sun and the earth is 1.496 into 10 to the power 11 meters. And the distance between the earth and the moon is also given to us as 3.84 into 10 to the power 8 meters. We have to calculate the distance between the sun and the moon. So from the figure, we can see that if we have to calculate the distance between the sun and the moon during solar eclipse, we have to subtract the distance between the sun and earth with the distance between the moon and the earth. So subtracting these two quantities that is given to us will give us the distance between the sun and the moon. So the required distance, that is the distance between the sun and the moon, can be calculated by subtracting the distance between the sun and the earth, that is 1.496 into 10 to the power of 11 with the distance between the moon and the earth, which is equal to 3.84 multiplied with 10 to the power of 8. And this distance will be in meters. So over here, what we have to do is, in case of addition and subtraction, for convenience, we have to convert these exponents into similar form. If we convert it in similar form, then that will be taken outside as common. So let's do that. So in order to do that, we have to convert this 10 to the power 11 to 10 to the power 8. For doing that, let's move this decimal point 3 places towards the right hand side. So when we do so, we are left with 1496 multiplied with 10 to the power of minus 3. This minus 3 has come because we have shifted 3 places towards the right hand side. Multiplied with 10 to the power of 11 minus 3.84 multiplied with 10 to the power of 8. Now, 10 to the power minus 3, 10 to the power 11. This gives us 10 to the power 8 because when bases are same, the powers will be added. Minus 3 plus 11 gives us 8. So we are left with 1496 multiplied with 10 to the power of 8 minus 3.84 multiplied with 10 to the power 8. Now we can easily take this quantity, that is 10 to the power 8, outside from both the terms. So we are left with 10 to the power 8 and within bracket we have 1496 subtracted with 3.84. So our final answer will become, like we have to subtract this quantity, and subtracting this gives us 1492.16 multiplied with this quantity, that is 10 to the power of 8. So we get 10 to the power of 8. And this is in meters. So we can conclude that the distance between the sun and the moon at the time of solar eclipse is 1492.16 into 10 to the power of 8 meters. So this is our final answer. Now in example number 8, we have to express the following numbers in standard form. The first example given to us is 0.000035. Now, in order to convert this small quantity in standard form, we have to shift this decimal place towards the right hand side and the exponent will take up a negative sign. So we have to shift it 1, 2, 3, 4, 5 places towards the right. So we have 3.5 multiplied with 10 to the power of minus 5. It will take a negative sign as I have already taught you. Now in this question, we have to express 4050000 in standard form. So in this number, the decimal point is over here. We have to shift the decimal point towards the left hand side. So we have to shift it 1, 2, 3, 4, 5, 6 places towards the left. So the answer will be 4.05 multiplied with 10 to the power of 6. It will be positive because we have shifted it towards the left hand side. Now that I have taught you the conversion of usual form to standard form, let's try doing the opposite. That is, converting the quantities from standard form to the usual form. So there are basically two important things to remember. One is, if this exponent or the power is positive. So in case of positive, we will be shifting the decimal place towards the right. And if we have a case where the exponent is negative, then in that case, we have to shift the decimal towards the left. So this is a very important thing that one needs to keep in mind while converting the standard forms to usual form. So in the first question, we have 3.52 multiplied with 10 to the power 5. The power over here is positive. So we'll be moving the decimal place towards the right hand side. So we have 3.52 multiplied with 10 to the power 5. Now this 10 to the power 5 means that we have to shift the decimal place 5 times, like 5 places towards the right hand side. So the answer will be, like we have to shift this to 5 places, 1, 2, 3, 4, 5. We'll give the decimal point over here and these gaps will be filled with 0. So we have the answer as 352000. So this will be the answer. What we did is, we simply shifted the decimal place towards the right because this exponent was positive. Now let us try doing the next problem, that is problem number 2. 7.54 multiplied with 10 to the power of minus 4. Now in this case, this exponent is having a negative sign. In case of negative sign, we will shift the decimal point towards the left hand side and we will be shifting it 4 places because it has 10 to the power of minus 4. So we will be shifting it 4 places towards the left. So let's shift it 1, 2, 3, 4. We'll give the decimal point over here and fill the gaps with zeros. 1, 2, 3 and a 0 over here. So the answer will be 0.000754. The third question that we have with us is 3 multiplied with 10 to the power of minus 5. Again, observe over here, the sign of this exponent is negative. In case of negative, we shift the decimal place towards the left hand side and it will be 5 places towards the left. So initially it is over here, we have to shift it. So on shifting this, we get 1, 2, 3, 4, 5. The decimal is shifted to this point and the places are filled with 0. So we have 0, 0, 0, 0 and a 0 over here. So our final answer will be 0.00003. So this is the final answer for in the usual form. So this was the end of the session and I hope you understood everything. In the previous lecture, I taught you about the basic concepts of exponents, the major laws of exponents and its application using various numerical problems, and we even learned how exponents can be used to express very large or very small quantities in standard form. In today's lecture, I'll be giving you a quick recap of all the concepts and formulas from starting to ending. So let's get started. The very first and the most important concept that I taught you was that if we have a non-negative integer a and it is raised to a negative power, that is minus m. So that can be written as 1 by a to the power of m. So in short, we can conclude that this negative sign from the exponent can be removed by taking the reciprocal of the base. So the first concept was very important and it will be applicable in many places. The second thing that I taught you was the major laws of exponents. The first law was that if we have two exponents with like bases and they are multiplied with each other, so then power will get added up. If we have a to the power m multiplied with a to the power n, then bases are same and they are multiplied, their powers will get added up. We will get a to the power of m plus n. The second law was if we have like bases and they are divided. That is, if we have a to the power m and it is divided with a to the power of n, then these powers will get subtracted. That is a to the power of m minus of n. The next law of exponent was an interesting one. Powers of power. So, if we have a non-negative integer a and it is raised to the power of m, and then this whole exponent is raised to the power of n, then what happens is that these two powers m and n gets multiplied with each other and will result in a to the power of m. The fourth law was that if we have a to the power of m and it is multiplied with b to the power m, that means the bases are not same, but the powers are same. So in that case, the bases gets multiplied up taking a common power, that is m. And this case was similar in case of division as well. If we have a to the power of m which is divided by b to the power of m, bases are unlike but the powers are like. So the bases will get divided taking a common power, that is a by b whole to the power of m. And another very important thing was that if we have any integer a and it is raised to the power of 0, it will give us 1. Any integer, if we have even 100 to the power 0, that will also be 1. Now, I even taught you about the application of exponents to express very small and very large quantities in standard forms. So that was very helpful in calculating very large and very small quantities, adding them up and even comparing one quantity with respect to the other quantity. So that was the end of this chapter, Exponents and Power, and the session as well. Thank you so much for joining me on Study Room. Hope to meet you in the next video with a brand new chapter.